Here is an introduction to astronomy to accompany Chapter 1 of the textbook Astronomy from Open Stax. Now, of course, this entire course is survey of astronomy, and we're going to cover many different topics in astronomy throughout the semester. But I wanted to take the opportunity to give a big picture overview of everything to try to put it all in context from the beginning so that when we cover the individual subtopics, hopefully you can already kind of see how they fit together with the whole picture overall. So what is astronomy? There's lots of ways to think about this. Astronomy, one way to think about it, it's the study of basically of everything, right? Or at least everything outside the extent of the Earth, but we also include Earth in terms of the properties that it has as a planet. So as Carl Sagan said, the cosmos is all that is, or ever was, or ever will be. So really we're studying everything here. It is an observational science mostly, so you can't conduct astronomy experiments, you just have to observe what's going on, and in that way it's much like geology, it's mostly observational. We can do some experiments, though these are really more in the realm of astrophysics, and these are computational astrophysics experiments, or you can do nuclear or chemical experiments. So this is mostly an observational science. You have to kind of take in what you can see and try to account for any biases that may be there, and it takes a lot of detective work to figure out what's going on. And astronomy is also an evolving field. So the main things that we're going to cover in this course, because it's an introductory course, and in this particular lecture, most of them are unlikely to change. A galaxy is still a galaxy. The basic properties of them are what they are. We know generally how a star works. But the details of almost everything that we touch on are generally not exactly solidified. So for instance, the details of the end stages of stellar evolution can be up for debate. Planet formation, not perfectly understood. Same with solar system formation. There's many interesting questions that still remain. So as with all scientific fields, when you're just taking a class, it may seem like this is all solved and we're just memorizing facts, but in reality, no, many of these are actually open questions that are still being answered. So as an aside from talking about any astronomical objects, we need to take a moment to talk about units and scales. So in astronomy, you have a huge range of time and spatial extents. So you're looking at time scales from femtoseconds, we'll talk about that in a minute, up to gigayears. Spatial scales, you're talking from femtometers up to very, very massive scales where basically you communicate about it in terms of light travel time. And so you need scientific notation because you're dealing with huge numbers. So it's basically, if you're not familiar, it's a more compact way of writing a very small or very large number. And what you do is you take your significant digits, the ones that you care about, and you basically put one of those out front, and then you move your decimal place over, and all the zeros or all the other ones go to an exponent. Okay, so the exponent basically indicates how many positions your decimal place needs to shift, and if it's a negative exponent, you're going to shift that decimal place to the left. So just as an example, what do I mean? That sounded probably a little bit abstract. Let's take this number here. We have 310 million. And 310 million, is a big number. It's not too huge, but it's still a little bit cumbersome to write out, right? It takes up a lot of space. So instead, we can take our decimal place that's on the far right, we can shift it over 8 positions, and because we've shifted it 8 positions, that then goes in the exponent. So this number, 310 million, becomes 3.1 times 10 to the 8. For a number that's less than 0, here's a different example. This is some very small number, and we can shift the decimal place over 10 positions, and then the decimal place goes from being where you can see it to in between the 1 and the 3, and this number we then refer to as 1.3 times 10 to the minus 10. So if you're not comfortable with this, please do see Appendix C of the Astronomy Open Stax textbook, because I'm just going to assume familiarity working with scientific notation. It's indispensable in astronomy just because of the size of the numbers we're working with. The system of units that we'll use is the SI system, though there are some specialized units that exist. Just in full disclosure, in astronomy, sometimes we use other unit systems. There's one called CGS that's a little bit different. You use centimeter gram second, but we're mostly here going to use the SI system because it's very common. So what this means, is for distances, we're going to express those in meters. So remember, a meter is about 3 feet, close enough. Time is in seconds, which you all know and love. And mass, we're going to express typically in kilograms, which 1 kilogram is about 2.2 pounds. We will often also express mass in terms of the fraction or the multiple of a planet mass or of a solar mass. And that's something that we're going to encounter later. So some SI prefixes that you're going to need to know, and you can see Appendix D for a more detailed explanation, are the ones here. So much like how scientific notation, we need a way to basically make big numbers and really small numbers more compact. We can do this with these prefixes as well. So this saves even more space. So rather than writing 10 to the 9 or a billion, we use the prefix giga. So for instance, a billion years is 10 to the 9 years, which is also a giga year. And similarly, 10 to the 6 is mega, that's capital M. Kilo, thousand, K. Centi is smaller than 1, right? 10 to the minus 2. You're familiar with the centimeter probably. This one's a little bit annoying in that this is case sensitive, right? The capital M is mega, the lowercase m is milli. So you're probably familiar with the millimeter, small. And then you can go even smaller, right? Micro, nano, and femto. And all of these are going to be used. So for instance, the age of the universe is in giga-years. The size of a nucleus is in femtometers. So we span this whole range. Some special units that we're going to be using, and we'll discuss these more later. For distance, we have 3 special units that are frequently used. So one of them is the so-called astronomical unit, named for its historical importance. 1 astronomical unit is 1 Earth to Sun distance, and that's about 10 to the 11 meters, or it takes light 8 minutes to travel that distance roughly. A light year is very commonly used in astronomy because it's a very vast distance, and we're dealing with huge distances in astronomy. So this is the distance that light travels in 1 year, which might sound far, but we'll see it's actually not that far in terms of the scale of the universe. So light travels at around 3 times 10 to the 8 meters per second. And so if you're covering this massive distance every second, you say, okay, how much distance did I cover in a year? So I multiply this number by the number of seconds in a year, and you get around 10 to the 16, 9 times 10 to the 15 meters. Another unit that's frequently used is something called the parsec. It's 3.26 light years. It has to do with when the distance at which 1 astronomical unit spans 1 second of arc. So it's a trigonometric kind of value here, and you don't really need to know how that's derived. Just know that it's on the order of a light year. Okay, it's a big distance. So what are the major components of the universe? What are the major players here when we're talking about different parts of the universe? So let's start small and zoom out. So moons, these are the smallest objects that we really encounter. So this is like our moon that you see, most nights. It's typically a cold rock. Cold's relative, but it's pretty cold. can also be, oceanic, depending. And this orbits a host planet. So the diameter of these things, are usually hundreds to thousands of kilometers. They're pretty big, but again, all things are relative. So this is the smallest scale we're dealing with typically in astronomy when we talk about a given object. And shown in this picture are to scale the four large moons of Jupiter. They're called the Galilean moons. Jupiter has many more moons. Then moving up, we have planets. So, moons are generally kind of tiny. Planets are often a good bit bigger, though the largest moons of big planets are similar to the smallest planet sizes. So it gets a little bit murky in terms of size, but what distinguishes a planet is this is, a relatively cold rock and or fluid, so it can be liquid or gas. It's large enough to be spherical. That's something you need in order to be defined as a planet. So the self-gravity makes it spherical. And it needs to clear its own orbital path around a host star. So it's circling a star, and there's not any other crud in its way. And those are things that define a planet. And you're typically talking about thousands to tens of thousands of kilometers in diameter. Then scaling up, you have a star. So this is the celestial object that planets are orbiting. So a star, this is basically a really hot ball of gas, mostly. And most of these are going to be powered by nuclear fusion. So there are nuclear reactions that are happening in the core of the star. And so that's what's powering these things and making them produce light. And these tend to be, light seconds in diameter. So the distance that light travels in a second is about their diameter on that order. So, around a billion meters or so. Then zooming out, you have galaxies. So galaxies are often hundreds of billions of stars. And so they're in a collection. They can have many different shapes. This is a interesting one called a spiral galaxy that is, we believe, our Milky Way is something kind of like this. Ours probably has more of a bar in the center. But in any case, it's a large collection of stars that are bound together gravitationally. And these galaxies are huge. They're the thousands or hundreds of thousands of light years in diameter. And then the galaxies themselves are collected into clusters. So if you look at the universe in our area, you have large collections of galaxies. And, they're in this local region, they're not necessarily homogeneous. There's an interesting structure here. If you look at large scales, there's structure, and we'll talk about that later, but you sort of have a homogeneous distribution of galaxies if you zoom out, or galaxy clusters rather, if you zoom out far enough. But this is the kind of spatial scale we're talking about, right? We're spanning many orders of magnitude, and these are the main objects that we're going to learn about in this semester. Okay, so if you didn't already appreciate it, space is big. Okay, and big is a total understatement. It's really big. So we talk about distances, in terms of light years frequently. And light speed might sound really fast, but this is relative to your distance that's going to be covered. So this is, for instance, looking at the speed of light relative to the size of the Earth, and this is in real time, not sped up or slowed down. So you're doing about 7.5 orbits of the Earth per second. So based on that, that's pretty fast, right? But let's just look at the light travel time it takes for light to go from the Earth to Mars. So when I first started talking in this slide about a minute ago, that beam of light was at the Earth. And we're a third of the way to Mars by that point, and now the GIF has restarted over, but it takes a long time even to go to Mars. And you saw that Mars is a relatively close planet to us, and if you zoom out, there are stars that are further away, galaxies are very large, so space is big, okay? So let's taking our light travel time, how long does it take for light to travel a given distance? So for light to go from the Earth to the Sun is 8 minutes. The nearest star, it takes light years to get to the nearest star. To travel across our galaxy, the Milky Way, 100,000 years. To get to the nearest galaxy, it takes 2.5 mega years, right? 2.5 million years. The visible universe itself, this is kind of a cheat, is around 14 billion years, is how long it took for light to travel from the furthest extent of the visible universe to us. This is sort of cheating because this is defined by the age of the universe, but nonetheless, you can see space is huge. And another interesting thing here is because we learn about space by collecting light, and it takes light time to travel, every object that we look at in space, we're actually looking back in time. That's a little bit of a handicap because we don't know exactly what's happening for any given object right now. We know what's happening a long time ago. But it's also an advantage because we can see how the universe has evolved over time by looking at objects that are further and further away. And so it's great, but if it weren't for this finite time, finite speed that light has, we would be hopeless in figuring out how the universe has evolved over time and how it's going to evolve. But because of this sort of time travel aspect of observational astronomy, we can know how it's evolved. Just another detail on the vastness of space. This is true when you have two galaxies collide. So talking about billions, hundreds of billions of stars. Two of these objects collide. None of the stars collide with each other. If they were just collections of stars, galaxies would pass through each other like ghosts. Basically, they would just interact gravitationally. Now, it turns out there is a lot of gas in between the stars, something we call the interstellar medium. We'll talk about this later. And so that gas does, in fact, interact and heat up. And so because space is so large, you've noticed there are these huge distances between, planets and stars, and then between the stars themselves and between the galaxies themselves. And so what that means is space is mostly nothing, okay? If you look at the density of matter in between galaxies, you're talking about maybe something like an atom or less per cubic meter. So take a moment to think about that. That is ridiculously dense. Space is mostly nothing. And so then astronomy, if you want to get philosophical about it, is the study of everything and nothing at the same time. So let's also, in astronomy, we have to worry about small scales as well. So we need to connect very small scales to very large scales. So stars, as we'll cover later, they're powered by fusion between atomic nuclei. So these are nuclear reactions. It's not like a nuclear reactor or most nuclear reactors, which are fission, where nuclei break apart. Here you have fusion. Nuclei actually sort of forced together, and that is a nuclear reaction that then can release energy to power stars and stellar explosions, and it also transmutes the elements. So at the beginning of the universe, as we'll talk about, there was basically only mostly hydrogen and helium, a little bit of lithium, a little mixture, maybe a beryllium boron, but mostly just hydrogen and helium. And then everything else was made in a star or a stellar explosion, with the exception of a handful of man-made elements. These were actually also made in stars and stellar explosions, but they have undergone radioactive decay, before people came around. So if we want them now, we got to make them on Earth. But nuclear reactions, these tiny objects, these femtometer scale objects, these are what are powering stars and the evolution of elements over time in the universe. Then if you go to slightly larger scales, you can go to chemistry. So there you're talking about angstroms, 10 to the minus 10 meters. Chemistry is still very important as well, because chemistry, it leaves an imprint on astronomical data, and it also gives us an insight into the conditions of astronomical environments, because we can do experiments on Earth to see when a certain chemical reaction can happen, what kind of conditions a certain molecule can survive. And so we can, for instance, use a telescope like the ALMA telescope here and measure light that indicates their molecular rotations and vibrations, and we can figure out that, hey, in this region, there are a bunch of organic molecules that were formed in space. So for instance, methanol. You have an alcohol, huge cloud of alcohol floating out in space. So the evolution of the universe, just in very broad strokes, and again, all of this we'll cover in more detail in subsequent lectures, but just as a general introduction to astronomy, this is the big picture evolution of the universe. So around 14 billion years ago, everything was essentially concentrated in a single point. And what happened before that, we don't really know. It's almost a question of philosophy and not even really physics at that point. For some reason, this point expanded in an episode called Inflation, a massive sudden expansion. And then about 400 million years later, stars finally began to form. So the matter made at the very beginning of the universe, that gas finally cooled enough that it could coalesce into spheres that eventually had nuclear fusion in their cores, and these are known as stars. And these stars, were located in different regions of space. Some are closer to others, and local density perturbations allowed the stars to collect together into objects that we know as galaxies. And going from just a kind of blob of gas and collection of stars to more formal galaxies and galaxy clusters, that took place over many billion years. In this time, basically when stars were formed, that's when planets could form as well. And we'll talk about that later, that star formation and planet formation in a sense go hand in hand. There's still billions of years separating them, but for this scale here, you can basically say you had stars, the stars were already grouping into galaxies, they were already beginning to form planets, and sometime several billion years ago, let's say 5 to 10 billion years ago, you had galaxies with stars in them that hosted planets. And that's basically what we see in the universe, and what we've seen recently is that the universe is actually accelerating apart. Everything is expanding apart at an ever-increasing rate, and so everything is kind of moving apart from everything else and in a broad scale. The reason this happens is because what the universe is comprised of. So most of what we're going to talk about in this class is mostly the atomic matter. That turns out is only a small fraction of all of the content, energy, matter content of the universe. We have energy and matter in one pie chart because you can convert between the two, right? That's Albert Einstein's E equals mc squared. But then a huge chunk of the universe is dark matter. We'll talk about that. That is key to understanding how galaxies are the way they are right now. The dark matter at some point, it made the universe kind of maybe start to contract a little bit, or at least stall in terms of expansion. But then dark energy has taken over, and we are accelerating apart. And I refer to these things very confidently, giving a name to dark matter and dark energy. But to be honest, we have very little idea of what dark matter is. We know what it isn't. It's not matter that interacts with light. We have some limits on its properties, but we don't really know what dark matter is. And dark energy we know nothing about. So then you might want to know, how do we know what we know, right? I've been talking very confidently here about all kinds of different aspects of the universe, things that are, very vast distances away. How do we know any of this? And it's mostly from light collected by telescopes. So just broadly speaking, we basically have spectra and light curves. Those are the two main things that we observe. So what a spectrum is, this is essentially the amount of light versus the wavelength. So what we have in this picture is a beautiful spectrum of the sun. The sun produces, or at the peak, light production is in the visible wavelength region, so the light we can see. And you're looking here at the spectrum of the sun. So really from long to short wavelengths would wrap red to blue, but it basically wraps around. So you can think about this as reading it like a book, left to right and wrapping around, and that's where it connects, and you're going long wavelength to short. What you see here, though, is that it's not uniform in intensity. So not only, and you can't really tell that here, but not only is the yellow and green more intense than the blue and the red, but you also have these gaps where there's not much light that makes it out of the sun at all. And this is something called a spectrum. The light curve for that, you'd be looking at the amount of light versus time. So if something got really bright and then dimmed, that's what you're looking at there. So telescopes collect spectra and light curves, for the most part, and that's how we learn about objects out in space. Telescopes themselves, you have many different types, and you're spanning the electromagnetic spectrum. So from very long wavelengths in the radio range, literally like the radio that you listen to in your car, all the way down to gamma rays, which are very high energy photons. And this is like the kind of thing produced in a nuclear reaction or a very hot environment. What this diagram shows here is that you often need a satellite if you want to be able to observe some of these wavelengths, and so that's why telescopes are both ground-based and space-based. So what's indicated here is the vertical direction, how far down a given color goes. That indicates how far into the atmosphere it makes it, basically, until it's mostly absorbed. And it's likely no coincidence that visible light makes it all the way to the surface of the Earth. A little bit of ultraviolet, a bit of infrared, so these mostly make it. But for instance, the higher or the shorter wavelengths, rather, X-rays and gamma rays, these are absorbed in the atmosphere. You need to send a space-based telescope up to observe it. Similarly, with some part of the infrared and the microwave, you need to have a satellite, a telescope on a satellite in space in order to observe this wavelength region. And then the radio, again, can penetrate through the atmosphere, and we can observe this with a ground-based telescope. These days, a hobby telescope might be something like 10-inch in diameter, but the most powerful tools of astronomy are large. So, for instance, optical telescopes, you're often talking about the active part of it being like 8 meters wide, pretty big. Radio can be even larger, can be like the size of a football field, and it's a bit hard to speak about the scale of these other types of telescopes because they're not probably exactly what you're thinking in terms of a lens and a mirror and whatnot. They get more complicated. But these are big objects. Nonetheless, you sometimes have dedicated satellites, or you can plunk these on the International Space Station. So some telescopes that are related to my research involving X-ray astronomy, these are located on the International Space Station. Note that there are some exceptions to how we know what we know. We can see neutrinos from the sun, and maybe from, we've seen them from exploding stars, and there's prospects from other stars as well. So neutrinos are very low mass neutral particles, so we get some information from those. Gravitational wave astronomy is a very recent subfield that has opened up, and that has taught us about very extreme environments, very high density environments, so we can learn a little bit from there. There's also meteorites, which tell us about objects in our solar system. So these are more or less rocks that fall onto the surface of the Earth. And then there have been some rocks and dust collected in space. So astronauts going to the moon, satellites being sent out to collect space dust. So there are exceptions, but for the most part, light is how we know what we know, and so what we're going to talk about soon is interactions of light and matter, so that we can then move on and learn more about astronomy. And that is it for this introduction to astronomy.